Okay, so tonight we're going to go through some centroids, just basic centroid stuff, dealing with rectangles, triangles, and semicircles. We're going to focus on some of the orientation issues that we have to deal with and that we have to monitor. So make sure we're paying attention to that kind of stuff. That's the key to what we're looking for today. All right, so what we have is we have a rectangle. Let's say it's 12 inches by 8 inches. Now what we're looking at is we're going to do, again, 12 inches by 8 inches. For a rectangle or square, what we're going to do is we're going to take the base, divide by 2, take the height, and we're going to divide by 2. So we're going to take the 12 and divide it by 2, and we're going to take the base and we're divide it by 2. What we're trying to do is trying to find the centroid location from basically the left-hand side, the bottom left-hand side of this rectangle. So from here to there, and from there to there. So when we do the 12 divided by 2, we're going to get 6. And when we do the 8 divided by 2, we're going to get the 4. So the x and y coordinate of that centroid is going to be 4 and 6. Perfect. We don't really need to worry about an orientation issue for rectangles or squares because it's just divided by 2, so it's always going to be the same. The key you have to pay attention to is when you do the 8 and you divide by 2, you're going to get the x coordinate, and when you take the 12 and you divide by 2, you're going to get the y coordinate. That's the kind of stuff you have to pay attention to with rectangles and squares. Now, triangles, you definitely have to pay attention to the orientation. So let's say this is 9 inches and this is 12. What we're going to do with triangles is we're going to take the base and we're going to divide it. Well, actually, let me just take a step back. For right triangles, you're going to take the base and you're going to divide by 3, and you take the height and you're going to divide by 3. Always with a right triangle. If you don't have a right triangle, then we have to do a little bit different of a situation, but we'll deal with that later. So we're going to take our 9, because that's our x dimension, and we're going to divide it by 3. And what that's going to give us is a dimension from that centroid to the left-hand side, or to the right angle of that triangle. So 9 divided by 3 is going to be 3. So that's going to be our x coordinate. We're going to do our 12 divided by 3, and we're going to get 4. Well, that's going to give us from the bottom of the triangle, which is where that right angle is, and we're going to get 4. So we're going to get 3 and 4. Now, what I want to show you guys is if I take that same triangle and I flip it into a different orientation, same distances, how does your numbers, how does your answers change? So 9 and 12, we're going to do our 9, we're going to divide by 3, we're going to do our 12, we're going to divide by 3. What we're going to get is a distance from the centroid, again, to that right angle. So here to here. That's 9 divided by 3, we get 3. But that's not the distance that they're usually asking for. They're usually asking coming from the bottom left corner, which is usually 0, 0 on the coordinate plane. So that's our x, and that's our y. They want to know what's the distance from here to here. Well, we know the whole distance from here to here. We know that is 9. So 9 minus the 3, and we're going to get an x of 6. Great. So we're going to get 6 is our x component. So then we're going to take our 12, we're going to divide by 3, and we're going to get 4. Now that distance comes from the centroid down to that right angle, which is down here. And what that's going to give us is 4. Now that distance comes from the axis, so we can use that. That's all we need. So 6 and 4 would be, so it was 3 and 4 here, and now it's 6 and 4, because that triangle has changed orientation, so it affects your answers. You have to pay attention to how those orientations are. Now, let's just do a quick talk about what happens when you have a triangle I apologize for my drawing skills tonight. But what happens if you have a triangle that has a line of symmetry to it? What do? Well, this is where you have to think a little bit. That centroid is going to fall on that line of symmetry somewhere. So, what I would ask you guys is, if this is 9 and the height of this thing is 12, we'll just do the same numbers. I would ask you guys, if there's a line of symmetry, how far is it from here to here? Most of you would say, well, it's 4.5. So that, in this case, is our x dimension. All we did was 9 divided by 2 because it has a line of symmetry. Now, is that always the x component? No, it's not. It's not the x coordinate all the time. It could be the y, depending on, again, how the triangle is oriented. So then how do you find this distance? Well, that's where you go right back to your regular triangle way and divide by 3. So on this one, it would be 4.5 and 4. Okay, so now let's talk about semicircles. Semicircles, again, have to pay attention to orientation. So let's say the radius of this thing is 10. So the radius of this semicircle is 10, and we'll call it a half circle. We know that centroid is probably somewhere about here. I think most of you probably understand that from here to here, there's a line of symmetry, so we're going to divide by 2, or we're just going to take the radius of the semicircle. Well, that's our x direction, so our radius is our x coordinate. So 10, that's our x. So then how do we find this? What we're going to do is we're going to do 4r divided by 3 pi. Now it's important that you separate those numerators and denominator, the numerator and the denominator, and do them separately, because that's the way the formula is formatted. So we're going to do 4 times 10 on the top divided by 3 pi. So we're going to get 40, and I believe 3 pi is 9.24, I believe. 9.42. 9.42. So we're gonna do the 40 divided by that answer, and we're gonna get 4.24. Now you have to think to yourself, is that distance from here to here down to that axis? Well, here's your y, and here's your x. The answer would be yes. So 4.24. Let's take that same thing and we'll draw it this way. Radius 10 again. How do our answers change? Because they definitely do. And they may not just flip-flop. We're going to find out. So from here to here, that's our y, and that's the radius of that semicircle. So again, the y, in this case, the y gets flipped. Now it's 10. And we're going to do 4r divided by 3 pi, and we get this distance. 4r divided by 3 pi gives us the distance from the centroid to the straight line of the semicircle. That's this. So that's this distance. What I would ask yourself is, does that distance go from the axis? Well, from here to here? Yeah. So 4.24 is our x. So indeed, this orientation to this, all those numbers did was flip. I don't want you to memorize that, though. I want you to understand and know just what you're looking at. Don't just try to memorize, because you can't. Because not every single one you're going to do is going to be like that. Now what happens if it's like this? Again, radius of 10. Centroid there. So, look, our y has not changed. It's still 10. Now, when you do the 4r divided by 3 pi, notice what happens now. Now that distance is from here to here. That's 4.24. That is not the distance we need, though. What we're asking is how far is it from here from those axes. So how far is it from here to here? Well, you have to think a little bit, but what's the radius of this entire half circle? It would be 10. So 10 minus the 4.24. 10 minus 4.24, and you're going to end an answer of 5.76. So that's how you do simple centroids. You got to really pay attention to the orientation. Make sure you're not just trying to memorize how to do triangles. You're trying to memorize the process on how to do triangles. So I can give you any triangle in any orientation, and you can work through it. You have to pay attention to the orientation of all of these shapes. That's probably one of the biggest key things you have to worry about with simple centroids.